Do I have to turn this on?
No, sorry, no.
It's on. Good morning. Welcome to the National Archives in Washington, D.C. Thank you for your time, and thank you for your interest in our presentation this morning. I'm Robert Chapman, Advanced Technology Research Activities of the National Archives for Electronic Records. It's my privilege this morning to introduce Dr. Regan Moore and members of his research team at the Renaissance Computing Institute and the University of North Carolina, where they'll present an update of their findings and developments involving the National Archives-supported Transcontinental Archive project and the iRODS technology base. So with that, it's my privilege to introduce Dr. Moore and your presentation. Thank you.
Fine. Thank you. Good morning. We're going to present technology today that's used to manage preservation environments that are intended to preserve records for the life of the Republic. This is a daunting task in that the technology we're using today we know will be obsolete tomorrow. One of our challenges then is ensuring that we have a highly extensible preservation environment that is capable of incorporating new technology next year while maintaining properties of the records that we're trying to preserve. The work that we're doing here is done under a project called the Transcontinental Persistent Archive Prototype. This is a distributed data management environment that incorporates storage systems at multiple sites in North Carolina, in San Diego, here in Washington, and at NARA in College Park. Records that are deposited into this environment can be replicated across the multiple storage systems. The system tracks properties of these records such that we can query the environment and identify how well the data are being preserved. It incorporates multiple types of technology such that the resources used at any particular location can be from different vendors. And it's doing this in the presence of a set of preservation policies which govern how we're trying to manage the data within this distributed environment. What we do to ensure preservation is install software at each location where we're going to store data. That software translates from what the client requires to the protocol required by the remote storage system. It manages a rule base at each storage location, which controls the policies for how you're allowed to access data at that location. And we have a metadata catalog that tracks all of the information generated within the environment. We query the metadata catalog to find out information about the records. We update the policies that are stored in this rule engine to change preservation policies over time. And we use this data server then to be able to interact not only with tape-based systems, but with file systems from Windows or Linux or Mac operating systems. When we consider the problem of preservation, there are multiple challenges. The central one we've been addressing in the Transcontinental Persistent Archive Prototype is that of infrastructure independence. We would like to be able to manage the properties of the records we're preserving independently of the choice of technology that's used for either storing the data or for choosing a database to store the state information or metadata attributes. Through infrastructure independence then, we can build mechanisms that allow us to incorporate new technology into this environment. And we'll have some slides describing how this is done. A second perspective is that what we're attempting to do is communicate with the future. We're trying to take records that we are preserving today, provide sufficient information for those records such that somebody in the future will be able to look at that context and interpret the records correctly. A traditional approach is to provide representation information from each record, and that's part of this Open Archival Information System standard. But in order for the system to work, we also have to provide representation information for the preservation environment itself. The task in the TPAP project then is to identify the policies and procedures which characterize what we're attempting to do when we preserve data, send descriptions of those policies and procedures into the future so archivists in the future can interpret what we've done and verify that the properties for authenticity, integrity, chain of custody, etc., have been maintained over time. So we're integrating information with the preservation environment and with the records that we send into the future. In the future, we read that information and verify that the system has worked correctly. In one sense, this is an end-to-end environment. We not only have to be able to characterize how we're managing and preserving the data, we have to be able to validate that the system is actually working correctly. The approach we've taken to do this is a generic approach that is actually applied to a wide variety of data management applications. For a preservation environment, there's a driving purpose. What are your intentions? What do you want to be able to claim about the records in the future? Based upon that purpose, we define the set of properties that we need to be able to associate not only with the records, but also with the preservation environment. Given those properties, we then define the policies that will enforce those properties. The policies define when and where we apply procedures, workflows, that actually do the data and metadata manipulation. The procedures we're running then do operations such as replicate a file, extract metadata, transform a data format, basically interpretations of the records that are needed in order to provide the correct representation information. Procedures then generate information that's stored in the metadata catalog. We can query the metadata catalog then to verify that the properties within the system have been maintained and have been set correctly. We also parse audit trails to track compliance over time. So given these mechanisms, we not only can define the purpose and the properties the preservation environment will maintain, but we can go in and verify that the system is working correctly. Within the transcontinental persistent archive prototype, we get to ask research questions for what are the correct sets of preservation metadata. What is the set of information I need to maintain to be able to verify the system is working correctly? What are the correct set of policies that you should implement? So if I have a policy for integrity, I also then need a policy for data replication. I need a policy to verify that those replicas are still good. I may need a policy for where those replicas may be deposited. So the simple idea of integrity may invoke multiple policies that the system needs to be aware of, that we need to be able to characterize such that an archivist in the future can verify that, yes, we did maintain the system correctly. The procedures are the functions that are executed when we invoke a policy. Those procedures are typically run at the remote storage location where the data reside. So if I bring a file into this environment, I may want to check its integrity. I'll have to calculate something called a checksum at the remote storage location to know that the bits within the record haven't been corrupted. Given that we have a set of standard procedures we can run, we then need these policies that verify assessment criteria. So this is an end-to-end environment. We're not only managing the ingestion, we're not only managing administrative functions applied to the data, but we're also validating assessment criteria for how well the system functions. To do this and implement the concept of infrastructure independence, we then have the following layers of indirection that are required within this environment. One of our challenges is that the clients, the mechanisms we use to access the preservation environment today, we know will be different tomorrow. So we need to be able to support a wide variety of clients, and from each client then, access the preservation environment, the software systems that are installed at each of the remote storage locations. Each time a client request comes in within the data management environment, there are some policy enforcement points where we immediately check, is there a particular preservation policy that should be applied? From that policy enforcement point, we can then invoke a standard set of procedures that manipulate the data, either do a transformative migration of the data format or manage replication. Each time we run one of those procedures called a microservice, it actually executes some I/O operations on that remote storage system. Instead of using the operating system protocol for doing I/O, we use a standard I/O protocol. And then we map from the standard I/O protocol to the protocol required by the storage location. That means the procedures we're running will run on a Windows platform or a Mac or any Linux or any of the different operating systems required for the preservation environment. So the data grid implements infrastructure independence. It's independent of the choice of the client. It's independent of the choice of the storage system and the storage protocol. If we have new technology in the future that uses a new storage protocol, we write a driver that maps from our standard operations to the new required protocol, and we can incorporate the new technology without having to change any of the components of the data grid or without affecting the user interface. Similarly, if we add a new client, we map from the client to our standard operations, and the new client will work on any of the storage environments that we currently have integrated. So we have not found any storage systems yet which aren't capable of being integrated into this environment. There are some very ancient systems that do simple get and put interfaces. To handle those environments, we put a disk cache in front of the storage system. Then we read and write to the disk cache. When we're finished, we do a put of the entire file into the remote storage location. So we're able to incorporate any type of storage environment by putting a disk cache in front. And we actually use that mechanism to be able to put data into cloud storage. We put a disk cache in front of the cloud storage, execute our policies on the disk cache, and then from there push the data into a cloud storage system that's available. So here's a very simple example which looks very complex. I've issued a client at the top called iPut. I'm putting a file into the preservation environment. Within the preservation system then, there are policy enforcement points. Each one of these is highlighted in blue, which are immediately executed based upon this action requested by the client. So the first things that happens is we're checking access controls. Are we allowed to access the system we're going to? Is there a public user policy that needs to be manipulated or handled? Is there specific access controls on this particular user? What resource are we going to put the data to? Is there a quota installed on that resource which controls the amount of data that can be written? How do we define the name of the file that's being written in that location? So this simple action of putting a file into the preservation environment invoked 10 different policy enforcement points. The line in black underneath the line in blue indicates which policy was accessed within the system. And then for those policies that actually had to do some work, there's a third line with an MSI, a microservice invocation, which identifies which procedures manipulated the system at that point in order to enforce the policy. So this perspective then says, based on the client action, behind the scenes, there is a large amount of work that's going on within the preservation environment to identify which policies to invoke and then to actually execute them. Apply those policies and modify or make dynamic decisions as required. So the lessons we've learned in building the transcontinental persistent archive prototype are mainly targeted towards implementation. The basic design of the environment that we've constructed has the required extensibility to incorporate new technologies, to implement the preservation policies we have today, to implement these procedures or workflows that are being applied at the remote storage locations. The implementation issues then relate to scalability. How well will this environment scale to 200 million to 1 billion files? How well will this environment handle very heavy workloads for reliability and robustness? What happens if we want to validate assessment criteria? How well can we parse audit trails to verify compliance over time? How well can we manage extensibility and ease of use? So what we'll present today is an interface which is the simplest possible mechanism we can construct for interacting with the preservation environment. It's basically a drag and drop interface. I drag a file or a folder onto a record series, and the system then automatically applies preservation procedures on that data, does all the right operations to preserve the data. A second challenge is how sophisticated does the environment need to be to address all possible procedures, all possible policies that a particular institution may want to invoke. And so we're going to look at the very simple characterization of how many clients are or what are the types of clients that someone may need to interact with the system. How many places should we be checking for policy within this environment? How many standard functions or microservices do we need to be able to compose your procedure you need to enforce your policy? How many different pieces of system information do we need to characterize the preservation environment? How many preservation policies themselves should be implemented? So we're going to look at behind the scenes the level of sophistication within the policy-based environment, the iRODS Integrated Rule-Oriented Data System, to implement the Transcontinental Persistent Archive prototype. So currently, there's some 35 clients that different communities use to access the data management system. The clients range from interfaces that are specifically developed, like Arch, for managing preservation policies, to interfaces that support traditional workflow environments that run on top of the system, to groups that have built digital library technology interfaces, such as Fedora, that runs on top of this environment. Web browsers run on top of the system. Web services run on top of the system. There are a variety of mechanisms that allow you to integrate this environment into your own directory or file system on your own laptop. So there are a wide variety of interfaces that different communities believe are the appropriate interface for their particular user group. When we look at this issue of policy enforcement points, each time we access the system from one of those clients, all of these policy enforcement points are live, can invoke a policy. So the policy enforcement points are independent of which of those clients you use to access the system. Traditionally, there are two policy enforcement points: a policy enforcement point to control ingestion and a policy enforcement point to control access. When we looked at all of the different operations needed for preservation, we've made a list of 71 different sets or locations within the environment where we should check for policy enforcement. They range from actions, which we know are going to be atomic. We're going to have an action to manage an access control. But we also discover that for many of these actions, we want the ability to do a pre-process on the data before we invoke the action, or we want to do a post-process on the data after the action is invoked. So if I put a file into the system, I could have a post-process for put policy, which allows me to automatically generate derived data products, apply transformations on the data, generate thumbnails of images, manage replication, etc. So this AC post process for put ends up being the policy enforcement point where a lot of the action occurs within the preservation environment. But there are many other things that could go on. There's a policy for what happens when you delete a user. If I delete a user that owns some files in this environment, do I first migrate those files to an archive? Do I take the files and put them under another user account? It's a policy that needs to be managed. Given those 71 policy enforcement points, how many microservices or basic functions do we need to implement all of the required procedures associated with those policies? So the goal is to be able to chain these microservices together to implement your preferred preservation policy. These procedures range from manipulating a file, extracting metadata from a file, registering metadata into the metadata catalog, replicating a file, etc. And so if we look at the current system, there are 229 such basic functions that we use to compose the preservation procedures. These functions are all operating system independent. They issue our standard POSIX I/O, so these same procedures run on a Windows file system or a Mac or a Linux or whichever environment you want to use. Given those microservices then, how many different attributes do we need to manage about the preservation environment and about the records in order to adequately characterize what's been happening, what's gone on in the system? So we end up having to manage attributes about the data grid, attributes about the users, attributes about the storage resources, attributes about the files, the data sets themselves, attributes about collections that aggregate those files, attributes about the rules or policies we're running, attributes about audit trails, attributes about load parameters, is a system being overloaded, attributes about the rules themselves, attributes about quota, and we end up in this case with roughly 205 system-level attributes that the system automatically manages. So these are attributes that the system typically generates and updates each time an operation occurs within the environment. So the system is managing this information on behalf of the archivist. The archivist can issue queries which then go in and look at the actual values related to these attributes for either the files, collections, or resources to be able to verify the properties of the environment. A typical set of policies we apply in this environment are organized by a record series. So we associate with the record series a set of preservation policies. Those preservation policies could be related to the authenticity procedures we will apply for records within that series, tracking the chain of custody, where has the data been placed, who has accessed, who's been allowed to apply a preservation procedure on the data. For managing integrity, if I have a corrupted file, the only way I can recover is to get a good copy from somewhere else. I need a replica. So the system has to provide policies for managing the replicas, verifying their integrity, managing updates to the environment, enforcing retention and disposition. If the lifetime of the record is 7 years, then we have to do the correct disposition policy after the 7-year lifetime. We're very interested in standards that are emerging for tracking trustworthiness. And the goal is to implement policies within this system to automatically validate the assessment criteria. So here's an example policy. I have a situation where a file has a retention period. So the system can get the current time, issue a query to our metadata catalog for a particular collection and ask, find all the files whose retention period has expired, i.e. the current time is greater than the maximum retention time. For each file in that list, then, we're going to delete the file, we're going to write out some information and track what we're doing, and we're going to post that information. So within this policy, then, you can control not only how you manage the disposition, but you can control what type of report you're going to generate, what action is performed upon the data, is it actually deleted, is it moved to an archive? All of that is controlled by a policy. So now we're going to switch to a live demonstration of the user interface and a web interface that allows us to set up policies for this environment. The procedure we're going to apply is we have a repository of rules that are available within the iRODS data grid. Now, each rule then is basically characterized as an XML file for what the input and output parameters are required for that rule. We can build a policy, which is a set of rules. And we can name that policy and store that policy, another XML-based description of those rules, in a directory within the data grid. We can then tag a record series with that policy such that the system then knows to identify the set of input parameters required for executing that policy, associate those input parameters with each record series, and then when I import a file into the environment, the system will automatically look at the properties on the collection and decide what should it do. So this approach allows us to define sets of policies, define which policies associated with which record series or collection, and the system then automatically enforces those policies. From the perspective of the user, all they're doing is dragging and dropping a file or a folder into the appropriate record series, and behind the scenes, the preservation policies are being enforced. So we're going to switch to a live demonstration, so we'll need to change that. In the live demonstration, we're going to be using a transcontinental persistent archive prototype node at the University of North Carolina. This is linked to servers here at NARA in Washington, D.C., to servers at NARA 2 in College Park, and to servers in the Rocket Center in West Virginia, and to servers in San Diego. This interface is called iDrop. This is a Dropbox style, drop a file into an interface. It sits up here in the system tray. So it can sit in the system tray of your operating system. And if you click on it, it will bring up the iDrop display. On the left-hand side, we see a list of collections that we have within the preservation preservation environment. We can select a collection, and with this central display then tells us which collections we can use to import data into. So we're defining the set of folders or collections within the preservation environment that we can use to drive data into. Over on the right-hand side, we can have the system look at the files that are present within the local system in which we're running iDrop. And if we pick a folder from the local files, we can drag it into one of these record series that have been defined. It'll be automatically queued, so now we're free to drag another folder into another record series. Every time we drag a folder in, the system can be queried to ask what's happening. So we can see that it's processing the files from the first folder, and there's a queue holding the files that were defined in the second folder. And then we can look at the status of all the files within a given process. So the system is automatically managing the transfer. It's tracking what happens to each file. It's giving us a status report of what's gone on, which files have gone successfully, whether or not we've encountered any errors within the environment. So from this perspective then, we're trying to interface, or a very simple interface, to our record series, which is strictly drag and drop. Behind the scenes, however, we have to understand how we associate policies with a record series such that we know what is being enforced within this environment. So we're looking at, I guess, the status of what's gone on. Yeah, that's okay. So some of the records are still being processed. Some are still waiting in a queue. Some of the records are complete. They've been transferred down to North Carolina successfully.
And this is in response to some of the concerns from talking with Rick and Mark, in the sense that this is also tracking per file any errors that occur either on the local file system, the network, or within iRODS. So you're actually collecting data as well about files that did make it over and for what reason, which
Yes.
is useful in a lot of different areas. And so if you think about it too, we're also collecting data from as it comes into the archive in terms of where did the files come from, where were they transferred from, and so forth. So this information also could be transmitted back to iRODS.
The next interface is the Arch interface, or archive interface. This is a web browser interface, that allows us to talk to the iRODS environment and set up policies. So Mike will go through a description of how he picks rules that will be associated with a policy, how he assigns that policy to a collection, and then we'll go back to the iDrop interface and show enforcement of a variety of policies on different collections.
Sure. Okay, so the emphasis here is on being able to use interfaces to declaratively define what policies are defined or are associated with a particular record collection or series, such that it becomes an interface that is understandable and usable by archivists or other types of users in other domains who aren't intimately familiar with the Unix command line or some of the subtleties of using iRODS. So what we're looking at here is something called Arch. Thank you. So this is the interface is called Arch, and it really sits on top of a toolkit that can be used to build different kinds of archival interfaces. And what we've done is we have set up an archive on IREN, the TPAP node at RENCI, and we have defined, in this case, a repository for policies. So you could have different roles within your archive setup, such that one person could define the policies for different kinds of records. The one example I was using would be the emails of the Chancellor of the University of North Carolina would be subject to a State of North Carolina email policy. So that email policy could be expressed using an interface that like this and stored, and then you could create a different series for the different years that his email traffic would go into. So I've defined a policy repository, and then inside this repository I'm going to add a policy, and I'm going to call this, I will call this email. And in this case, we're going to say that these records are virus scanned and the checksum is validated. Okay, so I'm going to place this policy into the repository. So what's actually happening is there's an XML document that describes this policy and then maps to rules and microservices running within iRODS. And so the policy is an abstract thing. It's sitting out there, and it then can be applied to different record series, and different policies can be selected, again, depending on the case. I'll add a second policy here, and I will call it, let's say it's, I'll just call it email 2 so I can find it. And in this case, I'm going to require a replica, and then I'm going to set a retention date. And I'm going to update again. So 2 new policies are added to this repository, of which we have many. Again, those policies are defined. They sit there in your archive, and then somebody whose role it would be, for example, to set up a new series could then go to this interface as a series administrator, and then they could add another series. And so what we're going to do is we're going to say email 2008, and we'll give it a path. Call it E2008 because I'm typing with one hand. And we'll select email, and we will update. So we have created a record series, and we have applied that email policy now to that series. And then I'm going to create a second one, and we'll call it E2 2010, let's say. Okay, and we'll E2, and we'll set email 2 as a policy. So 2 different series, 2 different policies. Okay. Now we're going to return to the iDrop interface, and we can see that there were transfers going on as we were talking. And that's one of the nice things about the iDrop interface is you can start your transfers, you can queue up many of them and leave it running. And the check mark here says that the transfers that we were doing at the first part of the demonstration are now successfully up on the grid. Okay, so what I'm going to do now is change the interface a little bit by selecting Show Policy Details. So again, clients do not need to be aware of policies that are sitting on iRODS, but we are trying to start integrating this idea of policy into the iDrop client. And so by saying show policy details, now the client is doing additional things to interact, let you know where, for example, what policies are applied to a series you're dealing with, and then information about how that policy is being enforced, status information, and so forth. So I'm going to go to this SAA demo, which represents an archive that we've created. And then I'll show here, for example, here is a repository of those policy files. And you can have those policy files distributed around your grid. And for example, if you create a new archive, you could actually say, I want this policy repository, and that would be the universe of policies that would be applied to the archive at hand. And then here is a directory under which we are placing, for the purposes of this demo, all the policies. And you can see some of the collections or series you see here have green flags. What that is saying is that those series are actually bound to a specific policy. And we're going to find, here is our okay, so E2008 was a policy where we applied the checksum validation and the virus scan. So what I'm going to do is I'm going to, for example, I have here a virus exemplar file. eCar, okay. So I'm going to take this virus exemplar file and drag it onto that collection and do a transfer. Okay, so the transfer is underway, and it's been successful. So what's happening when that transfer occurs, iRODS knows that a file is at that collection using, in this case, the post proc for put that Regan described, and then policies or rules are fired that know that that collection has a policy applied. The policy is consulted, the appropriate rules are then fired and using the correct parameters that are specific to that collection. So now if we go into the collection, we should see. Okay, so two things happened. One, when I did the transfer, I did not compute the checksum when I put the file into iRODS. And so you can see here that this represents the fact that there was a fixity check error, missing checksum. Okay, and then also, since this was a virus exemplar file, we can see that there was a virus scan failure on that file. So those were two different policies, again, defined through the web interface, applied to the collection, and then detected by the client. And then just very quickly, I'll go to the second. As you can see, we did a lot of testing before the demo today. Okay, and I will just grab a document, and I will put it on the second. Okay, so the transfer is complete. And I will note here too that you can actually see some of when the policy is applied. Here are some of the iRODS metadata that's linking this collection to the policy. So you can see it's hard to see up close, except up close, but there is a pointer from this collection to the policy file, and then since the policy is a template, there are data elements that customize that policy for the series that are also carried along here. So when you have, within iRODS, when you have a collection and an action, iRODS can find the policy, find the customizations, and also, again, find metadata that's been deposited that tells the status of that record through the workflow that's defined as part of your policy. And then we will just drop into this series. And in this case, the policies, this policy had a retention date, so you can see that a retention date has been placed on this record. And as well, we can look at replication, and we can see that in this case, we put the file originally on this loading resource, and based on the policy, the file has been replicated to RENC Vault 2.
Okay. There we go. I can hand that back. So what we've seen here is a simple demonstration of a very simple interface to a preservation environment where, even though we're just dragging and dropping files into the system, behind the scenes we're defining the policies, we're defining what needs to be done on each file as they're brought into a record series. One of the challenges, we almost made it. Let's skip down to, there we go. One of the challenges in building this environment then is there's a tremendous amount of sophistication behind the scenes that's needed to actually do this in a distributed world. So we're talking, in this case, we're running a system here interacting with the computer in Washington, but the data is going to a storage server sitting in North Carolina. To do that, we needed an environment which allows us to put our servers in front of every storage location where we might want to put data. We could just as equally well have put data onto a storage system in San Diego. We had to have a system that's managing the state information, our metadata catalog, so that every action that's done in the environment is tracked, and we know where the file was put, what the retention period is, whether it passed a virus scan. We had to have a messaging system because this is a distributed environment. We can have procedures which work on multiple servers. So part of the procedure is done on one server, another part of the procedure is done on a second server. We have to send messages back and forth to coordinate those procedures. We have to have a scheduling environment because we're managing rules which can be either executed immediately, as you saw in this case, or can be deferred to execute at a future time, or could be run periodically. So our assessment criteria typically are periodic rules that are run every day or every week. And the scheduler has to track a queue of those rules, execute them, send the required processing to the correct remote server in order to execute the procedure. And then within this environment, you pick your favorite access mechanism, whether it's a web browser or a file system interface for accessing the data that's in the distributed file system. The types of technology that we use in order to store the records then could be on file systems, they could be on tape archives, we could write data to a remote tape resource. They could be a cloud storage service, so I could put records into a cloud storage service and track properties on those records independently of the vendor. There could be local repositories. There are groups that are integrating traditional social networking repositories into this environment, so we can include them. And then you can store your data in your choice of, or store the attributes in your choice of the relational database. There we go. Yep. For the system to be extensible, it had to be highly modular, meaning that we can incorporate different authentication environments within the system. So there are groups that use Kerberos authentication, groups that use grid security authentication, groups that use Unix-based authentication, all interoperating. We had to manage authorization of every action within this environment. So any action requested by a client is being requested by a person who's first been authenticated, and then there are access controls that are verified to check what that person is allowed to do, and there are access controls for whether or not they're allowed to do it at a given resource. The system had to manage multiple types of transport because it's dealing with massive data. The system's designed to handle petabytes of data, hundreds of millions of files, file sizes that range from very small files, 100 kilobytes, to very large files that are measured in the hundreds of gigabytes. When you're sending a very large file over the network, traditionally to get optimal transfer rates, you then want to send multiple streams simultaneously. So it manages that. And the distributed rule engine then runs at each remote storage location. What this means is that when you interact with data that's at a particular site, the data cannot leave that site unless it complies with the policies that are also installed at that site. So you have a highly controlled environment where the participating institutions can control what's happening with their data, how they either manage preservation of data in concert with other members or how they share data with other institutions. The local rules apply. To look at the issue of scalability, we run performance tests on the environment. We continue to collaborate with multiple federal agencies for their use of this infrastructure. There are groups today that expect to manage 100 million files in the system. And the question is, how scalable does the system remain? Can I ingest data at the same rate, whether or not I have very small number of files in the repository, or can I get the same rate if I have 200 million files in the repository? So this test showed that on average, the rate increases slowly as you put more data into the system, or the number of files per second decreases slowly as you put data into the system. This is nominally putting in roughly 70 files per second, or 5 million files per day into the environment. And these particular cases where we see spikes where it takes longer to put the data in correspond to when the system is being taken over by other activities. So these are systems that have a maximum load they can support based upon the type of server you're using, the type of database you're using. Oops, back up. We do collaborate with multiple additional groups. The specific tasks within the TPAP project have looked at tuning the performance of the TPAP node so that we can support ingestion of large amounts of data. This required a fair number of analyses and implementation efforts to handle the load that was being put on the system, to handle the challenges of the particular networks we were dealing with. There are also challenges for tuning the database correctly to get the maximum performance, and then taking advantage of scheduling so that we do operations not only immediately, but queuing operations so they can be executed over a fair amount of time. One of the challenges in this environment is interoperability with other systems. There are multiple groups that are building data management environments, and they come up with standards for how they want to support interoperation with their activities. So an example is a BIGET container, which is one way of aggregating files and checksums for transporting to other communities. You can incorporate a mechanism within iRODS as one of these standard microservices that will automatically generate a BIGET container so you can move data to another site. Another group we work with is the University of Liverpool and the Shaman project, Sustaining Heritage Access Through Multivalent Archiving. This is a project in England that is also using the iRODS data grid, and they're developing technology to support their specific application environment completely independently of what we're doing within the TPAP project. But what they are doing, however, is they're integrating technology that's been developed by multiple communities into the iRODS data grid so that then those new pieces of technology become available to the entire world. One of the examples of doing this is they have mechanisms that manage the parsing, rendering, viewing, and transformation of a variety of data formats, and they have turned those mechanisms into microservices, which they call a media service, that can now be executed with an iRODS policy. So through collaboration with that group, we're able now to gain access to open source software that allows us to apply their data transformation mechanisms as microservices within policies controlled by our particular environment. So our goal then is to support a wide range of microservices, a wide range of policies that are developed not only within the TPAP project, but that become available from other institutions who are also applying the technology. We are working with multiple federal agencies. The technology that's being developed at NARA is of interest to other agencies. Each of these groups is faced with the challenge of preserving various types of data, from simulation output from computers, to remote sensing data, to observational data from telescopes, to climate change data. All of these communities have to face the issue of long-term preservation of their data. They want to be able to compare future analyses with the observational data they've collected today. So we're very interested in seeing that this technology is sufficiently generic and extensible that it can meet the policies and procedures of other groups that require long-term preservation or other types of data management applications. So I'd like to thank you very much for listening to this presentation. The work we've described here has been funded under research and development activities for the Transcontinental Persistent Archives prototype through the National Archives. Thank you very much.
Thank you, Regan. On behalf of David Fierro of the Archives of the United States, the National Archives, and our Center for Advanced Systems and Technologies, Regan and your team, thank you for your presentation this morning. If you have any questions about anything that you've seen or you've heard this morning, I welcome your questions. If you're joining us through the web or through the video, my name is Robert Chaddock. You can access me through email, and I'm certain that Dr. Moore and your team at the Renaissance Computing Institute would also welcome all questions that people
Yes.
may express. So with that, thank you all.
Fine. Thank you.
Thank you.